Test review for the definite integral. In question number 1 here, we're given a graph just made up of some lines forming some different shapes on the axis, and we're asked to evaluate several different integrals. In the first one, we're asked to find the integral from -4 to 2. So if I look at my graph, that's this area right here, starting at -4 and going to 2. So it's just the area of that rectangle, which would be 2 times 1, and that equals 2. For the next one, we're asked to evaluate the area from -2 to 2. And you can calculate this area. You can calculate the area of this triangle, and then this one, and then this one as well. But if you look at the graph, notice that this triangle and this triangle are the same size. And since the one above the x-axis is positive, the one below the x-axis is negative, their areas are going to cancel out. And the same thing happens with this triangle and this triangle. Their areas cancel out, and so you actually end up with an area of 0. In the next one, we're asked to calculate the area from 1 to -3. Notice that on this question, we are starting here at 1 and working back to -3. We're going in the opposite or negative direction, and so our area needs to be negative. We need to change the sign of whatever answer we get. Now, if I start here at 1 and go to -1, I'm finding the area of this triangle, which would be 1/2, has a base of 2 and a height of -1 because it is below the x-axis. Then I'm going to add to that the area of this triangle, which would be 1/2 times 1 times 1. And finally, the area of this square, which is 1 times 1. And so if we add all of that together, we get -0.5, or -1/2. In our final integral, we're asked to find the area from -4 to 4 of the absolute value of f of x. Now, the absolute value, all that does is takes these two areas that are currently negative below the x-axis. So normally we would consider that negative area. Since we're absolute valuing the function, we're making it positive. So for this final one, we're just adding up all of the areas as if they're all positive. So I'm going to add, first of all, this rectangle that we already know is 2. This little triangle, I believe we've already calculated that it is 0.5. This triangle, which is below the x-axis, it has an area of 1, which we've already calculated. This triangle between 1 and 3 is the same as the triangle between -1 and 1, so it's also going to have an area of 1. And then that final little triangle between 3 and 4, it is has an area of 0.5. And so if we add all of that together, we get a total area of 5. On question number 2, we are given the question says decreasing. This is actually a strictly increasing function. Sorry for that mistake. And it wants us to put these values in increasing order, meaning the lowest value first and the highest value last. So let's consider, first of all, the left-hand Riemann sum. I'll do that in orange, and I'm going to make 2 triangles, dividing this up into 2 from 1 to 2.5, and then from 2.5 to 5. If I make a left-hand Riemann sum, that's going to look like this, and obviously that is below the x-axis. If I do a right-hand Riemann sum, which I'm going to do in green, sorry, went a little too far there. The right-hand sums are going to look like this. Obviously, those sums go well above the value of the function. My trapezoids, those of course are going to be in between the left and right Riemann sums. And what's important to notice here is that our trapezoids are above the function. That's because our function is concave up. That means our trapezoids are going to end up above the function. So hopefully you can tell from the picture here that the lowest value is going to be the left Riemann sum. The next closest value would be the actual area between the curve and the x-axis. The next in order would be the trapezoids, and finally the largest value would be the right-hand Riemann sum. On question number 3, Buyer's Guide is testing braking performance of a Lexus. The test consists of using the brakes to bring the car to a complete stop when the car is traveling at 60 miles per hour. The velocity while braking is given in the graph below. So we have this velocity graph, and we need to notice that our units here are in miles per hour, and your units on the time axis are in seconds. So we don't have matching units, but the numbers that are given to us here on the graph, they're going to be a little more convenient to deal with. And so I'm going to go ahead and get an answer here and then just convert it at the end. We're going to use the trapezoidal approximation, 3 subintervals to estimate the distance necessary for the Lexus to come to a complete stop. Now notice I'm starting at time 0 and stopping at time 6. If I'm going to divide that into 3 subintervals, that means that each of my subintervals are going to be 2 seconds long. So my first my first trapezoid is going to be right here between 0 and 2. The next one should go from 2 to 4. And finally, the last one from 4 to 6, which actually ends up being a triangle because our final height there at 6 is 0 because the car has come to a complete stop. So let's do our trapezoid rule. For the first trapezoid, my 2 bases, remember the bases are the vertical sides. Our trapezoid is on its side. My bases are 60 and 55. My height is 2, and of course we're going to divide by 2. For my next trapezoid, I've got heights of 55 and 35. Still my height is 2, and I'm going to divide by 2. And for the final trapezoid, my bases are 35 and 0. My height again is 2, and I'm going to divide by 2. Now, if you chose numbers that were a little bit different than mine, like the 55 and the 35, it's okay if you're not exactly with my answer. If this was a multiple choice question, you would just pick the answer that was closest to what you got. If we do this calculation, we're going to get 240 miles. And obviously 240 miles is much too large of a number. And that's because of our time difference in our units. So 240 miles, we're going to divide that by the 3,600 seconds, because there's 3,600 seconds in an hour. And that gives us a final answer of 0.067 miles, which makes obviously much more sense than the 240. In the next question, after T hours, the population of bacteria is growing at a rate of 2 to the T 100 bacteria per hour. Write a definite integral that measures the total increase in the bacteria population during the first 4 hours. Then use your calculator to determine that increase in population. Notice they're giving us a rate function. It says here it's growing at a rate of 2 to the T. And if we want total population after 4 hours, we can integrate a rate to get that value. So I'm going to do the integral from 0 to 4 of 2 to the T dt. So that's the integral that's going to give me the population growth from 0 to 4 hours. And if you put that in your calculator, it's going to give you 21.640, and then if we put our units on here, it's 100 bacteria. Remember, they said that the units are in hundreds of bacteria. So really 2,100 bacteria is the population growth. Question number 5, a company purchases a new machine for which the rate of depreciation is given by this function dv dt as long as t is between 0 and 5. And the v is the loss in value of the machine in dollars after t years. The car was purchased new for $18,900. That's an important number. That's going to be our initial condition, the initial value of the car. They're asking us to write an expression that involves a definite integral and represents the value of the car after 5 years. Well, to find the total depreciation of the car, we need to integrate that function 500 times t minus 6. And we're going to integrate that from time 0 to time 5. But we can't just do that. If I put that in my calculator, it's going to give me a negative number which shows the depreciation and value. I need to add to that my initial condition of $18,900. And so if you put this whole expression into your calculator, it's going to give you a value after 5 years of $10,150. Question number 6. We have this graph shown below, and they're telling us here that region A has an area of 1.5. So this region right here is 1.5. Now, notice that region is below the x-axis, and so we might also want to note that it is negative. They're also telling us that the integral from 0 to 6 is equal to 3.5. And then they're asking us to evaluate these two integrals over here at the side. Well, in order to be able to do that, I need to figure out the area of B, region B. And in fact, that's what they're asking me to do in question A. So let's consider this integral that we're given. If the integral from 0 to 6 of f of x is equal to 3.5, that means that the area of A plus the area of B must be equal to 3.5. The area of A, we know, is 1.5. And so we can solve that equation for B, and we see that B is 5 if I add 1.5 to the other side. So this area has to be 5. And so that, in fact, is the answer to our first integral. The integral from 2 to 6, notice region B is from 2 to 6. It has an area of 5. Then question B asks, what would be the integral from 0 to 6 if we absolute value the function? Well, that simply means that this region A, which we've denoted as a negative area, we're going to change it to a positive area. We're going to add to it the 5, that is the area of region B, and we get 6.5. Question 7. The graph to the right shows the velocity of a car traveling along a straight highway. The car is 180 miles from Boston. Initial condition, this is where we're starting out, traveling toward Boston at time t equal to 0. Notice that the units on our graph, this is in miles per hour, and on my time graph we have hours. So what we have here is a velocity function, and we should note that we're looking at velocity. Question A asks, at what time does the car change direction? Well, if I'm looking at velocity, when velocity is positive, the car is moving in the positive direction. When velocity is negative, the car has changed direction. It's moving in the negative direction. And so you can see that that happens right here at time t equals 4. At that time, that's when the car turns around and is no longer, at first it's heading toward Boston, and then it changes direction, it becomes negative, which means we're heading back to where we started. Question B asks us to determine how many miles the car traveled between time 0 and time 3. And so if we're looking at a velocity graph and we're asked to determine miles traveled, distance traveled, we're finding area. So let's look at that area from 0 to 3. That's the area of that region right there. Now, as long as you have straight lines and good shapes, good geometric shapes that we know, you can divide up that area in any way that you want to determine. I'm going to cut it right here so that I have a trapezoid and a rectangle. that rectangle is going to have an area of 3, which is the distance along the time axis. Notice that each of the squares on the time axis represent half an hour. So this is 3 hours times 30 miles per hour. Plus, then we're going to find the area of this trapezoid. 1/2 base. So this is a trapezoid that's oriented in the normal position. My base is this distance here, which again is 3 hours. The other base is this distance right here, which is 3 squares, so that's 1.5 hours. And the height of this trapezoid is 2 squares, which would be 20 miles per hour. And if we do those calculations, we should get 135 miles. Now the next question asks, when was the car closest to Boston? When was the car furthest to Boston? And did the car ever reach Boston? Well, the car is the closest at time equal to 4, because it's at that moment when the car turns around and starts heading back to where it started. So in order to find what that distance is, we need the integral from 0 to 4 of this velocity function. Well, we already know that the integral from 0 to 3 is 135 miles. We just calculated that in the previous section. And we need to find the area of this triangle that is remaining. That triangle has a base distance here of 1, and its height is 30 miles per hour. So that gives us an area of 15, and if we add those together, we get 150 miles. So that means that the car traveled 150 miles toward Boston before it turned around and went back. Next question is, when is the car furthest away? And our possibilities there are that it's furthest away at time t equals 0, because it starts out 180 miles away. The other possibility would be at time 7.5 hours, because in this time right here, the car is traveling back to where it started. And so we need to find out how far back the car traveled, which means we need the area of this region. So this triangle has an area of 1/2 times 1 hour and a height of 30, we can put our negative on at the end, 30 miles per hour. And then the remaining rectangle has, let's see, this distance is 2.5 hours. And again, my height is the same of 30 miles per hour. If we add these together, we get 15 plus 75, which would be 90 miles, which means the car traveled back towards where it started 90 miles. Now, when it turned around, we'd only traveled 150 miles, which means we were still 30 miles away from Boston. If I add to that another 90 miles traveled back in the other direction, that puts us at 120 miles away from Boston, which is still not as far as the initial 180 miles. So we were furthest at time t equals 0, because that's when we were 180 miles away from Boston. And finally, did the car ever reach Boston? No. The car was 30 miles away from Boston when it turned around and headed back. Final question. The Fish and Game Warden is responsible for stocking the pond diagram below, or in this case to the right, with fish before the fishing season. To determine the appropriate amount of fish, the warden needs to determine the volume of the pond. The warden determines the distances across the pond at 200-foot intervals. So that means the distance between each of these intervals is 200 feet. And those distances that he's measured are in the diagram. He knows that the average depth of the pond is 20 feet, and we're asked to calculate the volume. Well, hopefully you remember from geometry that volume is equal to the area of the base times the height. The height in this case is going to be that depth of 20 feet. We just need to find the area of the base, or in other words, the area of the top layer of the pond. Well, with these measurements that we have, we can use trapezoids to find that area. If I'm connecting each of these endpoints together, you can see that we can make trapezoids that would help us estimate this area. So I'm going to start up here at the top, and of course this one would just be a triangle since one of the bases is 0. So 1/2 times 520, and the height of that triangle and the height of all of our trapezoids is going to be 200. Next one, 1/2 520 plus 800, again times a height of 200. Next, 1/2 800 plus 1000, again times a height of 200. And obviously if you wanted to do this 1/2 and 200, like factor it out on the front and just add and multiply together all the bases, you could do that. But I'm going to keep going in this way since I've started. 1/2 times 1000 plus 1140, again times the height of 200. And then 1/2 times 1140 plus 1160 times 200. Plus 1/2 times 1160 plus 1110 times 200. 1/2 times 1110 plus 860 times 200. And finally, 1/2 times 860 times 200 for that last triangle. So let me just make sure I got them all. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. It looks like I got them all. If we put that in your calculator, do so very carefully, you should get an area of 1,318,000 square feet. So that's the area of the surface of our pond. Remember, our goal was to find volume. Volume is going to be equal to that 1,318,000 square feet times the height or the depth, which is on average 20 feet. And that calculation gives us a volume of 26,360,000 cubic feet.